Hello, operating systems people. Today we're going to be talking about memory allocation. This is actually going to start the second major part of the class, which is talking about the spatial aspects of resource management rather than the temporal aspects of resource management. I'm Gabe Parmer. Hopefully it's going to be fun to learn about how malloc and friends work. So what is the motivation here? At its core, as an operating system, we need to in some way manage the memory of the system, right? And memory when we boot up is actually corresponds to the DIMMs that you see on the right? These are the actual RAM that we put into our system. So this is what we call physical memory, and it's really just a big old array of bits going from 0 to the amount of memory that you have in your system. If that's 8 gigabytes, then it's from 0 to 8 gigabytes, right? And the big question to start out is really just, can programs execute with this memory model? Is that all that we need? We boot up a process, we started executing directly on physical memory, and we're good, right? Are we done? And if the answer is no, or there are complications, how should the operating system actually manage memory? What are the problems, and how do we split it, etc., etc.? So let's dive into these details. One analogy that you might think of is from the Matrix, which is that every single virtual address space within the system is kind of a process, processes its own little world, right? So what does that mean? A virtual address space is something that we've talked about a lot in this world, and it points to the fact that physical memory is not enough. The physical memory is the real memory executing on your system, and a virtual address space in some sense is fake. We haven't talked yet about how it's provided, but it is virtual in some sense, right? So the question is, why do we need this? Why do we need virtual memory as opposed to simply executing directly in the physical memory of the system? And of course, the idea here is that the matrix is about control, so an operating system also is trying to maintain control by providing an abstraction of being able to own all memory on the system to each process when in fact they do not, right? So we've talked about virtual memory a lot. We still are not going to talk about how it is provided yet. That's in 2 lectures. But we have seen this abstraction where we have our text or code loaded into the system, we have our data, we have our heap which grows upwards. There's a big hole in the virtual memory, and then we have some sort of stack growing downwards. And this is really what we see on XV6, where we just have this big hole in between the stack and the heap, and addresses within the virtual address space going from 0 to 3 gigabytes. Now what this implies is that malloc and free manage the heap, which is to say they need to somehow know how to expand upwards with the arrow, and they also need to understand how to manage the memory that they have actually allocated from the system. Now, this is not what it looks like in all systems. Even on a 32-bit system, Linux looks something more like this, whereby address 0 is null, and we need a hole around null so that if we dereference it, we have some sort of a fault. Then we have our code, our data, our heap, which grows upwards. Somewhere in the middle of the address space, we actually have a lot of libraries that get loaded in. And then if we have a multi-threaded process, we have multiple stacks executing within that virtual address space. So I'm simplifying here, but the big point here is that we need some way to dynamically allocate and free memory. And though the heap grows up and we can ask the operating system for memory, we still need something to manage that memory within the heap. And this is typically where malloc and free come in, right? But let's take a step back from that and ask some very basic questions. We know that there are stacks within the virtual address space. We know that there's the heap within the virtual address space. So what part of the system actually manages each of these? I'm going to let you think about that. We've already talked a little bit about the heap. I'm going to let you think about that for a second, pause the video, come back. So the stack grows downwards, we know that, but the question is, how big should your stack be, right? Do we statically allocate a stack of like 32 megabytes or something? Well, probably not. That's a lot of memory. Do we statically allocate a stack of 4 kilobytes? Yeah, probably not. That's not enough. So do we somehow magically need to know the maximum size of the stack that every process needs? That's probably also not a great idea as well, right? So somehow we need to more intelligently manage this stack. And how much stack size a process needs is very dependent on its usage, right? If it has a lot of local variables within stack frames that are large, then it's going to need a larger stack. If it has recursion and recurs quite a bit, it's going to need a larger stack. If it doesn't do either of those things, 16 kilobytes is probably more than enough, right? So, because we cannot tell how big it's going to be, at least in Linux, we use what's called expandable memory. So when we allocate memory, we can kind of tell the Linux kernel what type of memory it is. And if it's an expandable region, then that means that if we get a page fault, an exception for accessing memory that is not present within our virtual address space, directly below a region of memory that is expandable, the kernel will actually allocate more memory for us. So this enables the stack to effectively automatically grow, which is pretty cool. The heap, as we've kind of already talked about, is implemented in malloc and free. But it's important to ask yourself what is malloc and free's implementation, right? Is it library calls? Is it system calls? Whatnot. You could imagine that malloc and free are actually system calls. And if they're system calls, then that means that we are actually calling down to the kernel every single time we call malloc and free. Now remember, our proxy for calling down to the kernel is something like 100 cycles. So this is adding a significant overhead onto every single one of our allocations. And this is not generally something that applications want to have to pay for every malloc and free. We really, really want malloc and free to be on the order of, 20 cycles, not 100 plus the implementation, right? They're very, very frequent in many applications. So, because of this, malloc tends to be implemented in a library, and to expand the heap, it uses system calls, sbreak in xv6 or mmap in Linux, to allocate more memory that the library can then manage. So there's this nice separation where the library is essentially managing what's effectively kind of the cached memory up in user level that it has previously received from the kernel, and we call down to the kernel effectively only when we need more memory or we're willing to give it back memory that we don't need. Okay, so given this, we're going to explore how to implement that library today. If we wanted to implement malloc and free in user level, how would we do it? The lab corresponding to this is going to talk about how malloc and free is implemented in xv6. But for today, we're going to talk about advanced means of doing this that are used within Linux and other systems. But to get there, we have to really understand what the goals of heap allocation are, right? It's obvious that, okay, we want malloc and free to do the functional thing that they're supposed to do, right? Not a problem, of course. But we also kind of want them to do more than that, right? We want them to be fast. We want to efficiently use memory, whatever that means. Think about what that means. What does it mean to effectively use memory? What does it mean for it to be efficient? Ponder on this a little bit. Penny might be a little bit too tired and comfy to actually be able to contemplate that. But you can and should. Please pause, think about it, come back. Okay. So, yeah, we want efficiency, we want good memory usage, which effectively means minimal waste. Waste is effectively memory that cannot be used for allocations because it's used for something else, right? Efficiency means, yeah, good asymptotic notation, but in this domain, in the malloc domain, it usually often means a very, very low constant time. So most of the effort goes into minimizing the constant overheads, not necessarily getting rid of the asymptotic ones. And the big question that is really, really hard to answer is effectively, where do you keep the data structures that are going to track your allocations? And to point out why this is difficult, you have to realize that we can't malloc data structures to track allocations because we're implementing malloc. So you have this weird chicken and egg where malloc needs to track the allocations in the system, but because it's implementing malloc, it cannot call malloc to implement those data structures to track the allocations in the system. Okay, so let's look at this a little bit. Here we have our heap. Our heap has not yet had any mallocs happen in it. In fact, what's happening right now is we're calling sbreak and asking it for 4096 bytes of memory, a page worth of memory. So this might be when the program starts executing, or it might be when there's no available memory within the memory that we previously asked for, so we need to ask the kernel for more. So sbreak, we're actually calling the kernel and saying, hey, give me some memory, and it returns us this region, which is in this case 4096 bytes. Now what we're going to do is use that heap to allocate a whole bunch of times, right? So in the top time of the timeline, we malloc once. The second step, we allocate 3 more times. The third step, maybe we've freed a couple of those previous mallocs. And then the fourth step, we want to be able to malloc and use one of those regions that was previously freed. This is why we're doing this in a library, so that we can malloc from previously freed regions and therefore do not need to make a system call whenever we need more memory. On a system, it's probably safe to say that most calls to malloc do not make system calls, because if you're in a system that does malloc and free a whole bunch, you're going to be able to reuse those previously freed regions of memory for future mallocs. But I want you to observe here kind of the difficulty in this, right? How does our malloc implementation know where those free chunks are so that it can malloc within it? When we malloc within one of those free chunks, how do we choose which of the 3 free chunks within that timeline to be within third timeline to be able to choose? These are the questions that we need to answer in implementing malloc. So, okay, how do we do this? How do we track? Let's start with trying to answer the question of how do we track these free holes within the system, right? So in the top of the timeline, the first timeline, we see that there's 1 free hole, that's the rest of the heap. In the second timeline, we see that there still is only 1 free hole within the system that could be used for a future malloc at the very end of the heap. After we call free a couple of times, we can see that there are now 3 free holes, and then even after we do a malloc, there still are 3 free holes, right? So somehow we need to track these free holes so that they can be used for future calls to malloc, right? And the big question here is simply, when free is called, how do we know how large the memory chunk that is being freed is? So this is a little weird, right? Because the free API only passes in a pointer that you want to free. It doesn't include how big that memory that you're freeing is, right? It's up to the implementation to somehow track that. So how do we possibly do that? You know, your brain may go to like, well, maybe we need a binary tree to track all of the free holes, right? Or we need some sort of a linked list to track all of the free holes within the system, so that we can look up within that when we get a pointer, and we can see how big that region is. But if we're going to implement a binary tree, if we're going to implement a linked list, the question is always, where do we get the memory for that data structure? We are implementing malloc. Therefore, we can't rely on malloc to get our data, right? So we need to implement the very logic that tracks our own data structures. This is why malloc is unlike a lot of other things in the system, and why malloc typically needs to be implemented in some sort of a memory unsafe language like C. So the big idea here is that if we want to track the holes, we can observe that each of the free regions in memory, the free holes of memory, they are not currently used for anything. They are not currently used for any of the current memory that's been allocated out in the system because by definition they are free memory, right? So all of the gray, dark gray boxes here are malloc memory. They are used for current mallocs. However, the dotted light gray allocations are free. That memory should not be accessed by the user in any way, shape, or form. So the big realization here is that we can actually use it for a data structure. And this is where we actually can implement a free list. We can use the first portion of each of those free regions to hold the free list data. And the free list is effectively a linked list that tracks all of the free memory in the system. So it's a linked list, as you can see by the arrows here, and each of those nodes within the linked list that is placed at the beginning of each of those free regions includes the size of the freed memory, so that we know how big that freed memory is, we know how big of a malloc it can satisfy, and of course all of the linked list information. This might be next in previous if we have a doubly linked list, right? So this is a free list of memory allocated within the free nodes of the memory itself, which is kind of crazy to think about, right? But it's not quite enough, right? It allows us, when we call free, to have some sort of a data structure, in this case a linked list, which we can use to kind of walk through the linked list to try to satisfy a future malloc. You can imagine malloc might be implemented by simply walking through the free list and trying to find a hole that's large enough for the requested size and using that memory correspondingly, right? So in the third step of the timeline here, that's what we do. We get a malloc request that is relatively shorter than the size of that second hole. So we allocate the memory, and because there's some difference between the size of the hole and the allocated memory within that fourth timeline slot, we simply create a smaller residual free hole within the system. But it's not enough, because when we call malloc, when we call free, we actually need to be able we need to be able to know how big the memory that we're freeing is. So a free list allows us to implement malloc because it tracks all of the free memory. But when we free a node in memory, we know that it's going to create one of these free holes and we should add it to the free list, but we don't know how big that memory should be. Remember, free does not pass in a size. So the free list we can use to help us aid in malloc, but we still need something additional to let us know when we call free how big the memory is so that we can add it correspondingly to the free list. Brainstorm a little bit about how this might happen. Pause, come back. Okay, so when we want to free memory, we simply need to know how big the memory being passed to free is. We only get a pointer. We don't know how large it is. So what we actually do is right before the memory returned from malloc, we can replace a header. And that header is effectively the size of the actual memory itself, right? So effectively, when we call, I'm sorry, I lost my track of thought there. I forgot what I was saying. I'm going to start again. We have this header at the start of each of the allocations so that when we call free, we can simply kind of go back in the memory to find the header from the actual pointer itself. We know the pointer starts till the start of memory, and directly before that is the header, which tells us how big the memory is. So now we can actually track the size of each of the allocations, simply because literally there's a small data structure directly before each of our pointers that we're returning from malloc, which is kind of clever, right? it may be a little kind of mysterious how to actually implement lists. It's a little difficult to think about what this might look like in C, because now we have this header like directly before an allocation. So it might help to kind of think about the code looking something like this. When we call malloc, we walk through a free list and find a free chunk of a corresponding size. We update the free list, all of that stuff, and we kind of put the header within that memory. Now, of course, now this means that we need to allocate a free size, which is the size requested plus the header size, right? So we're actually taking up some memory for the header, of course. But in malloc, after we allocate that size and after we've updated the header to include the size of the allocation, if we want to return the address directly after the header, the code above simply does that, right? We look up the memory value right after the header and return its address, right? And then in free, when we actually want to discern where the header is so that we can figure out how big the memory chunk is so that we can add that chunk onto the free list, you can see the code for free where we essentially take the pointer that is passed into free and find the header, which is directly before in the index directly before that pointer. Now, of course, you can do this with pointer arithmetic too, but I always find it's easier for people to typically think about array operations, even if they're negative, right? So with just this little bit of clever pointer manipulation, we can track how big allocations are so that when we free them, we know how big our memory we should free. And we know when we want to implement malloc, we know how to track a free list, which is all of that free memory in the system, which is really cool. You could actually, using just these two techniques, go out and implement your own malloc right now, and it's not that far from XV6's malloc. However, there are some advanced techniques that actually even XV6 does that we want to consider. And to give you some intuition as to what those are, imagine that in the bottom timeline here, where we have the free node, 2 allocations, and then a free node, imagine if that first allocation there was freed. What we really want to do, instead of having 2 free lists, 2 items on the free list, one after the other, what we really would want to do is actually have one larger free item that includes the previous free list and the new contribution to the free whole within memory, right? So let's look at what that might look like. So you can see that we've called free with the orange memory. I'm highlighting orange in the timeline there. And you can see that what we're really trying to do if we're freeing that chunk of memory is we want to actually say, is the memory directly before this, the chunk of memory before this allocation, is it free? And then same thing after it. If the memory before is free, then we want to combine that free chunk or that free whole with now our newly freed memory. If the memory after is free, we want to do the same thing there. This is called coalescing. So what we're doing is we're taking multiple free regions and coalescing or combining them into one larger free region. So we're going to talk about how coalescing can work effectively. So what we typically want to start by asking is just this question here, which is that region of memory directly before us free? Yes or no? If it's yes, we combine. If it's not, then we don't. And is the region of memory behind us free? Yes or no? Etc., right? So we have the data structures down below, and to actually answer this question, the most direct way to do it is actually probably just to add a bit effectively within the header and within the free list so that we can effectively see, is this free or not, right? So you can imagine that the free list entry is that bit is always set to 1. For the header of an allocated range of memory, it's always set to 0, right? So now we can actually tell whether that chunk of memory before and after us is free, therefore we should coalesce. But we still have another question. And that question is just, how do we find these two data structures before and after us, right? In this example, we have a freelist node before us and a allocated header node after us. So we need to find both of those somehow so that we can simply ask this question, look at their is free field, are you free or not, and should we coalesce? So to find the one after us, it's actually pretty simple because we have our header that we're already looking at. It tells us how big the allocated memory chunk is. So what we can do is we can effectively take our address, look the memory chunk size into memory to find that next node, be it a free node or a header, right? And because now we can find that address of that next node, we can ask whether it's free or not. In this specific example, it's not free, so we are not going to coalesce, right? But it's a little bit trickier to figure out where that previous node is, right? So how can we actually figure out where the previous node is? So the next node, we don't coalesce, it's not free. The previous node, we need to actually add a little bit more intelligence. So we need to add, one example of how to do this at least is to add a new field into each of the memory headers, which is the size of the previous chunk, right? So now we actually know not only how big our chunk is, but also the size of the previous chunk in front of us. So now if we want to find that previous freelist node, we can find our own address and then the previous chunk size in front of us to actually find that node, and we can ask, is it a free node? We can look at its is free field, and of course, because this one is free in this specific example, we could add our newly freed data into one larger freelist node with that previous node as well. So you can see we've kind of made this much larger freelist node, which is great. But this wasn't free to do, right? It wasn't free to do because we had to add more memory to each of the header and the free list. The free list, it's not memory that's used for anything else, so it doesn't really matter that much, but the size of the free list does impact the minimum allocation size that's possible. So you can never really make an allocation that's smaller than the free list node itself, because when you freelet memory, it couldn't hold a free list node if it was smaller. So you need to be a little careful there. So the free list node size does matter, certainly, but not nearly as much as the header, because when the header gets large, we kind of have a problem. The amount of we are allocating the header size plus the malloc request size every time that malloc is called. So kind of by definition, the header is just kind of wasted memory somewhere, right? So this is not great. So we'd really like to be able to do something more intelligent, right? So, we might repeat this whole thing for an operation like this. So let's look at that let's think about that optimization as we kind of follow this through another example. If we get another free request and we want a free list region, then we now have an interesting case. We need to coalesce not just with our previous free region, but also our next free region, because there's a free region before and after us, right? So we need to somehow just figure out whether, we need to coalesce with those things before and after us. And a difficulty here is effectively, how do we actually, when we need to coalesce with something that's already on the free list, in this case, the second item, we need to actually remove it from the free list because we're coalescing it with essentially what's the previous item on the free list in this case. And there are kind of two ways to do this. Either we use a doubly linked list or we have a sorted list, which is what XV6 does. So if we have a sorted list and we want to get rid of that second node there that is currently on the free list because we're deallocating this chunk, then we just need to walk through the linked list and kind of, get rid of that node to make it look like something like this. However, if we don't want to keep that node sorted usually requires an O of n cost in this context. If we don't want an O of n cost and want everything to be constant, then we might actually need the free node to be a doubly linked list. Okay, so now we're kind of talking about more complexity for the free list and maybe even making the free list node size larger. So this emphasizes our point that we'd really like to minimize the size of all of these things, and a lot of the cleverness that goes into a lot of these algorithms is effectively for how we can actually minimize these types of sizes while maintaining O of 1 in a lot of different places. So hopefully you've been following me up to this point. At the highest level for kind of how we track a header with every piece of allocated memory, and a free list node and a free list for all of the free chunks throughout memory, and generally how we can convert something from a free list node into an allocated node, and from an allocated node during the free operation into a free list node while we're coalescing with previous and next free holes. Now I'm going to dive into some of these optimizations that I was referring to. And if you want to see kind of a tour de force in applying a lot of these optimizations, see DL malloc, Doug Lee's malloc, which is kind of a prototype implementation, or the prototypical, I should say, implementation of this style of a memory allocator. And the first thing to realize is that this is free. Integer, as we have here, is taking up a lot of memory, right? An integer is usually 4 bytes, and we're literally using it as a bit. So the first thing that we want to do is effectively figure out how we can take that effectively bit and just put it into one of the other fields. So in a header, what this effectively means is maybe our memory chunk size. The most significant bit of that is effectively whether it's free or not, right? So this is essentially a way for us to choose is free or not. Now, the second thing is, again, remember that the header size is really important, because the header is it's strictly wasted memory in addition to every memory allocation. When we are allocating out memory, we take the size passed into malloc, add on the header size, and that's how much memory we need to find and use for that allocation. So we really want to get rid of that previous chunk size variable in there, which you see in the bottom left. So how could we get rid of the previous chunk size within the header? Remember, we're trying to use that to identify the size of the previous allocation. Penny is getting very, very excited about previous memory sizes. Okay, so how we can do this is we can effectively also track in the header and the free list effectively whether the previous, or in the header, sorry, whether the previous value is free or not. So this means that our header for an allocation tracks whether the previous is a free node or it's an allocated node, which of course means we need to update that if that node changes its status. So this is effectively another bit that we have to use. In addition to whether this node is free or not, we now need an additional bit for whether the previous is free or not. Okay, so we simply have another bit here that tracks that. That's fine. Again, in the header, we could kind of use that as the two most significant bits within memory chunk size track those two values, right? Realistically, the memory chunk size is probably a multiple of 4, so the least significant bits within memory chunk size are always 0, so we could use them, but I'm using this as an example. If we know that the previous allocation, the previous memory span before us is free, we know it's a free list node, then we assume that directly before our header is a footer for that previous free allocation. This is shown as yellow within this picture. and that footer includes the previous size. So this allows us to effectively put that previous size, which we need somewhere. We need to know how big that free allocation is in front of us. It allows us to put that into the free memory that is not being used for anything else and take it out of the header itself, right? So if we know that the previous node is free, then we know that we can look an integer in front of us to find the previous size, which is the yellow nodes here, and then we can use that previous side to find the red node in front of that, which is the freelist node, right? Okay, so that's interesting. That's fine. That allows us to effectively get rid of this previous chunk size variable. It allows us to get rid of both of the bits. And that's effectively pretty good. We're actually not wasting that much memory at this point. So I want to go back and just kind of remind us how we got to where we are, right? Let's go back here. So at the start, we have one allocation in the very top timeline. So it's an allocation, therefore it has a green header, and we have the red that is tracking the free window of memory, the free hole of memory at the end of the heap. Three more allocations means that we've allocated 3 more chunks of memory, which means 3 more headers preceding each of those memory allocations, and the free memory has shrunk. If we free the first and the third allocations, we need to add them onto the free list. What that means is that we need to, during the free operations, figure out how large each of those allocations were so that we can add those chunks onto the free list. In the bottom part of the timeline, when we do another malloc allocation, we can walk through the free list to find a hole that's large enough to satisfy that allocation and convert it into a memory allocation, which means basically allocating size for a header plus the requested malloc size, and shrinking the free hole after it, right? So this is effectively what we want to do. And if we do some subsequent frees at that point, as we have here, we want to be able to coalesce those newly freed holes with the previous holes as we see here, right? And if we free more nodes, we want to coalesce them, in this case, with the free holes before and after, removing the before and after from the free list and having one larger free hole on the free list so it can satisfy a larger future malloc allocation. Okay. So the question now is effectively that we have a free list and we can use that to do a future allocation. So malloc will happen, and when malloc happens, we need to figure out which one of those free holes we can use for a malloc allocation. Now, first fit is the most intuitive. We simply walk through that linked list of all of the free holes, and we allocate the first hole that's big enough. So again, in this example right here, we have in the third step of the timeline, we have a big free node. We get a malloc that fits in that node, and because that is the first free hole that can fit that new allocation, in the fourth step of the time series, we see that it's been allocated there. So that might be following a first fit style allocation methodology, right? But there are different allocation methods. So there's also best fit. Best fit means that we iterate through the entire free list and find the free hole that best fits our current request. That means that the difference between the size of the free hole and the amount of memory that we need for this allocation, the size passed to malloc plus the header, is the smallest. So the best fit means the smallest residual hole after the allocation, right? But then there's even worst fit, and worst fit is allocating through the entire list, finding the allocation that results in the largest residual hole after the allocation and uses that. So I want you to think a little bit about what we're trading off in each of these cases. What are the benefits and downsides of each? And essentially, what are we actually trying to consider as what's good and what's bad, right? So think about this for a little bit. Pause the video. Best fit, worst fit, first fit. What are the pluses and minuses of each? Okay, so first fit, it's O of 1, or it's O of n in that we need to walk through the free list. But once we find a hole that's big enough, we're done, right? So asymptotically, it's O of n. If I said it's O of 1, I apologize. I didn't mean to. It's O of n. So that's bad, but at least from a constant perspective, what is the practical overhead of this operation? When we find the first hole that fits us, we can use it, right? Best fit and worst fit, that's not the case. It's O of n, and it's actually, overhead of n. We need to walk through the entire list to figure out which is the worst or the best fit, right? What are some of the other trade-offs that we have there? We don't really have a mechanism to think about how well we're using memory, but you can imagine best fit, because it's going to be leaving the smallest holes after an allocation. Maybe that's good for memory utilization, right? Because it's kind of effectively trying to find the hole that best fits us. The irony here is that people have run simulations and have shown that over time, best fit actually doesn't do that well, because it does create a lot of these very, very small holes that cannot be used for a future allocation. So best fit or worst fit in the long run might actually provide better utilization of memory, because they result in a fewer number of these small little holes within the free list that can't really be used to satisfy a future malloc, right? So we have a rough idea of kind of asymptotic complexity, a little, just kind of the constant time, expenditures of both of these, first fit versus best fit. But the question is, there have to be better ways to do this. Are there more intelligent free lists? For instance, ones that, try to actually get to O of 1. So the answer is yes, of course. The answer, and this is Penny powering up and going Super Saiyan, obviously. It's actually her Halloween photo, because, we're getting to that point. And she can be a little terrifying. I know that when you all see her now, you're being trained to be like, oh god, there's a question, I must think, therefore scary pooch. So she's just owning that, right? Super Saiyan Penny is best Saiyan. So are there more intelligent ways to manage the free lists, right? Now, I want to emphasize here that I'm not modifying anything that we just talked about in terms of the headers, the free list. Like, all of those techniques are still now used to track memory, but just the way that we're organizing the free lists now completely changes, okay? So, how do we manage the free lists? If we want constant time allocation, then we can use a lot of the intuition that we got from the second homework, where we essentially said, okay, priority queues are important. I'd really like to make an O of 1 priority queue to use as an operating system run queue that can be O of 1 time complexity, right? This is the foundation of the so-called O of 1 scheduler in Linux. We use that same intuition and say, oh, okay, I know how to make something O of 1, so long as there are a constant number of buckets that I need to iterate through or look through, then I know that I have constant time. So we can use that intuition and fragment our free list and have a free list for different sizes of chunks of memory. So in this case, we could have a free list for chunks of size 16 bytes. We could have a free list for chunks of size 32 bytes, 64, 128, 256. Now we're tracking these different buckets for the different sizes of memory, and we're choosing ranges of memory based on powers of 2, right? So that means that if we want we get a malloc request for a size of memory that is between 16 and 32 bytes, between 17 and 32 bytes, we would look up memory within the free list for 32 bytes. If you receive a malloc request for 33 bytes to 64, we would choose it within the 64 byte free list, right? So you can see we're doing something weird here, right? Even though there's a malloc request for, let's say, 50 bytes of memory, we're looking up in the free list that contains all allocations of size 64 bytes. Okay, so there's something weird going on here where we are not actually allocating memory of the requested size. It could be larger than the requested size. But it means that when we get an allocation request of 50 bytes, because power of 2 arithmetic has intelligent ways to manipulate it with, bitwise and XOR, all of that stuff, we can actually, in constant time, after a very small number of operations, figure out which index we should use within this array very quickly in constant time, and look up to see whether there's memory in that free list very quickly, because we only need to pull something off of the head of it. So this is not just O of 1, this is not just constant time, it's also exceedingly fast. We do a little bit of bitwise manipulation on the requested memory size to figure out which bin we look up in, let's say 64 bytes here, and then we remove one item from the linked list, which is of course O of 1, just essentially setting the head to the next value. So this is exceedingly fast. This is about as fast as you can potentially get. Well, that's not true. Bump pointers, feel free to look them up, are faster. But this is almost the fastest that you can possibly get, right? But everything's a trade-off in life. Nothing in an engineering domain is better along all dimensions, right? So this is brutally fast, O of 1 with a very, very small constant factor. But what's the downside? Think about it for a second, pause, come back. So of course the downside here is memory utilization, right? We are allocating a 64 byte chunk of memory for a requested 50 byte chunk of memory. If we ask for 65 bytes of memory, well, we need to use one of the chunks that is of size 128 bytes, right? So if you think about it, the worst case amount of memory that we are essentially wasting here is essentially 50%. We could ask for a 65 byte chunk of memory, and we need to spend 128 bytes, which is which is a little bit less than twice as much. So we're wasting effectively 50% of memory in the worst case. How much memory are we wasting in the average case? Well, that's completely different, right? In the average case, it's you can take what is the amount that we're wasting in the worst case, 50%. What's the amount that we're wasting in the best case? 0%. What's kind of the average between those? Well, on average, we're wasting 25% of memory using a power of 2 allocator. Informally, most modern mallocs are okay wasting about 12.5% of memory. So this is not that, right? This is more than that. So how do we think about this memory wastage in a little bit more principled of a way? Well, we want to think about the allocation that we want to think about memory being efficient in terms of asymptotic overheads and constant time. In terms of memory wastage, we think typically of fragmentation. Fragmentation is broken into two conceptual ways of thinking about fragmentation. One is external fragmentation. In the initial timelines that I showed you, all of those holes left behind by freeze are external fragmentation. That is wasted memory due to the memory allocation algorithm and the pattern of mallocs and freeze. Internal fragmentation is essentially wasted memory due to the difference between the actual amount of memory allocated for a specific request. That's important, for a specific request versus how much was requested, right? So if we request 65 bytes of memory and we're allocated 128, well, the internal fragmentation is 128 minus 65, right? 63 bytes worth of internal fragmentation wasted, right? Okay, so let's go back and think about the different allocation algorithms. We saw that first fit, best fit, worst fit leaves holes within the address space. And effectively, what I said before was that best fit can leave a lot of small holes, which is essentially that cannot satisfy a future malloc request. This is essentially saying that best fit can cause holes that lead to persistent external fragmentation between different implementations. However, the amount of internal fragmentation is very small because we're effectively allocating exactly the amount necessary for a given request, modulo the header, right? However, the power of two allocators, they have a large amount of internal fragmentation, right? They have a large amount of internal fragmentation because if I request 65 bytes, then I have to allocate 128. The difference between those is the internal fragmentation. So in the example, again, the holes in the allocations are external fragmentation. The amount that those persist and the sum total amount of that memory is the external fragmentation wasted within the system. Whereas if we make a malloc request for 90 bytes, well, we need to use 128 byte bin in power of 2 based allocators. So the amount of internal fragmentation is 38 bytes till the 90 allocated, right? So that's internal fragmentation for a specific single allocation, how much memory is wasted, whereas external fragmentation is due to the pattern of mallocs and frees and how we kind of choose which region of memory to choose for those mallocs. Now, there is something that I'm not really talking about here, and that's effectively that if we have two contiguous n byte allocations in a power of 2 allocator. So we have two of these that are contiguous within memory. Should we be able to coalesce those into an 2n allocation? So if we have two 64 byte allocations that are contiguous, one right after another, and they both are free, should we be able to combine or coalesce those two allocations into one 128 byte node and put it into the 128 byte free list? Obviously, we kind of want lists because otherwise it may end up that everything kind of ends up with a lot of external fragmentation. But we'll go into next time what that actually means. So, in summary, when you're implementing malloc and free, you need to be really clever about how you're storing your data structures and what you're doing there. And no matter which way you look, there are kind of trade-offs. These trade-offs are typically between the memory utilization and the efficiency of the algorithm. We'll see next time that those span also to parallelism and the API, how easy the API is to use. We saw that there are a number of algorithms for this. First fit, worst fit, best fit, these are all O of n. First fit is O of n, but at least kind of practically faster because it uses the first allocation. In these types of techniques, we actually kind of went over the coalescing algorithm, right? It's pretty straightforward so long as you can figure out the size and whether the size of the previous allocation, whether it's free or not. So this coalescing is kind of free, but in power of 2 allocator, we saw that it's exceedingly fast, O of 1 and very small constant factors, but it can have a very, very large internal fragmentation, and your intuition might say that it's relatively complicated to do coalescing within the system. So we will look next time at an effective way to do that coalescing. I do want to mention here that though what we went over today does have a very large internal fragmentation, there are power of 2 allocators that effectively do power of 2, but then have another bin between each of the powers of 2. And what this does is effectively, because now we don't just have power of 2, we have power of 2 and then a midway point in between each of the powers of 2. you can see that it actually is going to end up having about a 12.5% average internal fragmentation. But I'm not going to go into that. Next time, we'll talk about specialized allocators and more of these trade-offs. Hopefully you enjoyed learning about how memory is allocated, about effectively how malloc and free are implemented. All right, until next class, have a good one. Bye-bye.